In the example we've shown here, we have 3 different DSL routers. The y-axis shows the round-trip time, or the latency, to a nearby server in milliseconds, and is again shown in a log scale. We started an upload at the time 30 seconds, shown on the plot. Now you can see that different modems experience a huge increase in latency when we start this upload. Some of them experience a latency of as much as 1 second, up from a typical latency of about 10 milliseconds. One particular modem saw a round-trip latency of as high as 10 seconds during uploads. Now, to remind you what's going on here is that the modem itself has a buffer. Your ISP may be upstream of that buffer, and your access link may be draining that buffer at a certain rate. TCP senders in your home will send until they see lost packets. But if the buffer is large, the senders won't actually see those lost packets until this buffer has already filled up. The senders continue to send at increasingly faster rates until they see a loss. As a result, packets that are arriving in this buffer see increasing delays, and senders continue to send at faster rates because without packet loss, they don't have a signal to slow down. There are several solutions to the buffer bloat problem. One is obviously to use smaller buffers, but given that we have a lot of deployed infrastructure, simply reducing the buffer size in deployed routers, modems, switches, home Wi-Fi devices, and so forth is a tall order. The other thing that we can do is to use the traffic shaping methods that we've learned about. Consider that the buffer drains at a particular rate, which in this case is the rate of the uplink to the ISP. If we shape traffic such that traffic coming in to the access link never exceeds the uplink that the ISP has provided us, then the buffer will never fill. Thus, by shaping traffic at the home router such that the rate that traffic is sent to the ISP never exceeds the rate of the uplink, the modem buffer will never actually fill up. This type of shaping can be done on many OpenWRT-capable routers, including the Bismarck routers that we've developed here at Georgia Tech.